Hello, thank you for coming to this talk on Overwatch's animation pipeline. My name is Jesse Davis. I'm a senior animator on Team 4. I've been with Blizzard for almost 5 years now. On Overwatch, along with hero production, I was primarily responsible for the look and feel of first-person animation, outsourced content supervision, and the design, workflow, and cohesion of the animation team's pipeline and tools. This talk serves as a broad introduction to the workflow and tools of our pipeline that we use day to day. We'll first take a look at how a new IP, team culture, and Blizzard values help guide the direction of the animation pipeline. Then jump to the foundation of our animation system and how we use animation layers to assemble our heroes. Next is on to our new animation template system with an overview on the different ways an animator assembles a hero's performance. Then we'll take a look at one of our most important tools, the hero rig, and its creation. Let me start my timer. As well as some functionality built into the rig that greatly improves production speed. We have some general Maya production tools as well as some engine tools to share. And then finally, some thoughts for the future and where we'd like to go from here. Before I begin, I'd like to give a big thank you to everybody on Team 4, the Overwatch team, for creating such a great platform for animation, and to the animators and artists for producing the content shown in this presentation. Also, thank you to the team leadership for making tool creation a priority on Overwatch, allowing for a higher quality of life on the production side. Anyway, let's begin. Hopefully you're at least a little familiar with Overwatch, but if not, Overwatch is Blizzard Entertainment's newest fast-paced 6v6 hero-based shooter. Here's a partial clip from the gameplay preview trailer our team presented at BlizzCon in 2015. Should be sound, hopefully. There we go. So, where does an animation pipeline begin? Well, to throw out a little short-term history, about 4 years ago, after the cancellation of Project Titan and trying out a bunch of different prototypes for new ideas, the team agreed that we loved the idea of a hero-based shooter. While we had some ideas and tools that could carry over from our previous project that would fit with the new design, there was a lot of infrastructure needing to be revisited. The new IP presented a lot of unanswered questions with answers that seemed to be quite a ways out. But the most positive and decisive trait that formed during our project reboot were strong culture-paced foundational pillars and resilient beliefs on how we wanted to make this game together. Our team culture had a very compelling impact on the direction Overwatch took throughout development, and more relevant to myself in this talk, the animation pipeline. A general goal of the teams early on was an attempt to keep headcount low and to maintain the intimate feeling of a small indie team. And as Jeff Kaplan, our game director, puts it, we wanted to maintain a smaller size to be tight-knit enough to maintain or to minimize bureaucracy and maximize individual creativity. Early on, we wondered how we could keep a team small, specifically animation, and support a wide variety and range of body types, all without drowning from asset explosion. Day one of this project, we had all these questions. What would our heroes look like? Would we have aliens, monsters with 10 arms? Who inhabited this universe? We don't really want everyone to have the same body shape. That might make everybody feel a bit more generic. What does that mean for animation style and fidelity? Will we have to bring on 20 animators to get this thing out the door? Previously on Titan, we learned how scope could quickly be blown out with added features and nice-to-haves. And implementing features that weren't core to finding the fun wasn't something we wanted to be spending our money and limited time on. Applying these lessons to Overwatch's animation, we immediately recognized that asset explosion could quickly bury us if we weren't careful. We needed to focus on what was most important and minimize the extra fluff. This only build what we need pillar is core to our production pipeline. Another pillar early on, specifically for the art team, was that we wanted to emphasize a handcrafted art style. While this ideology mainly came from moving away from the more modular kit pieces we had for environments, we wondered if this mantra could help guide the animation workflow as well. Above, you can see some of the similar size body type heroes that we ended up coming with. If we had maintained this body type size for all of our heroes, it might have made it more easy for production, but it gets away from the diversity of the cast that you see below. We wanted to deviate from similar sized body types to get this level of personality throughout all of our heroes. So, in summary, a pipeline was required that supported a wide variety and range of unique character proportions and body types, multiple limbs, tails, etc. for heroes and abilities, like dragons, all while maintaining a realistic budget, and allowed for a small team size that did not sacrifice on quality but still lived up to that level of Blizzard polish and handcrafted art style that we've all come to expect. That's not too bad, right? Well, let's fast forward to present day. While we've definitely grown on the animation department over the course of production, I feel like we've significantly reduced potential headcount through picking and choosing our asset battles and through the use of technology to mitigate risk and reduce iteration time. On the top, you can see where our animation team started about 4 years ago. On the bottom, you notice that we've only really brought on 6 more animators and 2 additional riggers and skinners. Looking back, I feel like we could have made a substantial increase in headcount had we picked and chose different asset battles. So let's talk a little bit about how some of our philosophy reflects our production pipeline and implementation stuff. This slide shows the performances we consider high visibility. You'd see these in most of the moment-to-moment gameplay. To maintain that level of Blizzard polish without asset explosion, we would spend a majority of our animation time on these moment-to-moment gameplay performances and come up with other solutions that rely on animation technology for our less visible performances. A handcrafted art style to us meant crafting every high visibility character performance uniquely, such as the runs which you see here on the right. In essence, ensuring each hero feels unique with their own personality. As you can see on the left, sharing something like a run across multiple characters, like kind of what some military-style first-person shooters do, can give a sense of generalness and reduces the amount of opportunities for personality in the character. Not only was this mentality important for creating believable characters for a new IP, it alleviated concerns we had early on about each hero needing to feel different when played. No 2 heroes should feel like they ever overlapped. After Titan, we also implemented a new pillar for our animation production. The animator would be fully responsible for the entire in-game performance of our heroes. We made a departure from incorporating the TDIA, technical designer and animation role we had on Titan. Jamie Jeffcoat gave a presentation at GDC in 2015 on the role of a TDIA at Bungie. She describes the role as a cross-disciplinary bridge between animators, designers, and engineers who works to support and build the animated world of Destiny and sustain content requirements. She makes a lot of great cases for incorporating this role into a production pipeline, and I suggest if you're interested in learning more about the role to check out her talk. But for us, we decided to go a different direction. So for Overwatch, while this did mean there was a higher learning curve and onboarding time for new animators joining the team, there were in turn fewer middle parties between the animator and the in-game performance of the character. I believe this philosophy empowers the animator, as they are responsible for the character performance as the player experiences it. It also provides many opportunities of growth artistically and culturally. Artistically, this workflow allows the animator to think of the character as a whole, how it moves as a performance, rather than just a bunch of single animations strung together in sequence. As shown here, an animator responsible for assembling the assets shown on the right can produce a unified character performance as represented on the left. This ensures the highest quality overall character performance, as the animator's eye is best for judging the character performance itself. I also believe this brings us closer to using the game as a truer medium for animation, and as such, emphasizes our handcrafted art style pillar even further. And as a side note, since the animator is more aware of how the performance is authored, I believe this also has the side effect of lowering the turnaround time on bug fixes animators can solve on their own, as well as raising the amount of bug fixes the animators can solve permanently, just because they're more experienced with the technology and implementation. So culturally, having the animator responsible for their implementation is an opportunity for the collaboration with almost every discipline on the team. These disciplines in turn are able to provide input back into the animation, but furthermore gain the same opportunities to learn about how animation relates to their discipline, allowing more trust and fewer mistakes between departments. We all make better choices for each other. On the slide you can see as an animator, I work almost with every discipline on the team, depending on the task, of course, on a day-to-day basis. Animators aren't just building in a box when they're free to collaborate. They can work directly with designers and engineers to ensure that gameplay comes first. So gameplay first, and the next 3 slides are kind of Blizzard's cultural pillars. They're our mantra to making games day to day. They're actually engraved around that orc you see right there in our courtyard. Interacting with other disciplines day to day helps create and build relationships with team members outside of the animation department. This collaboration creates a more social work environment. An animator gains a larger circle of influence on the team through input and discussion with other disciplines. It also provides greater opportunities of ownership within the animation team, as well as giving experience to under-the-hood tech, to learn and grow as a game animator. When all of these factors are combined, an animator comes away from the project having gained core skills essential to the game development process, and thus becomes a better game developer. And having an animator with more skills, more ownership, and more control allows for that animator to contribute at a higher quality level. So let's talk about how some of the technical developments reflect these philosophies and cultural goals. Try to get some water. One sec. Most in-game performances of the character are a culmination of animations. Is that playing? Go. While there are some full-body animations that play as authored, assembling animations together allows for more reuse and eliminates a lot of the need for the brute force approach to creating assets. In Maya, animation layers like the ones you see here combine to create a single reload animation. You can see them highlighted in red. There's a bunch of shaking animation layers and a primary reload animation layer. In game, however, many animations can layer to create a single performance. So for example, here would be a typical reload suite we would need to author if we were to approach a reload performance through only full body animations. To cover all possible directions in a reload for idle, we would need 9 separate animations. We can call this a brute force approach. And here are the assets we would need to create if we were to create the same performance by layering animations. You can see we have one central reload and one set of aims. By making choices that take advantage of gameplay mechanics and using layered animations, we can break up the animation or the performance up further so that you get all the motion of the full body physicality but with fewer assets. For example, in the idle reload, we don't need to communicate to the opponent where you are aiming, and therefore have the freedom to blend off the additive layer that controls the aiming and simply play the center reload instead. If for some reason the 2 assets do not work together, body physiology, gameplay requirements, and weapon design can all be contributing factors. We have the opportunity to use more assets. I'll explain how we do this in a moment, but this is a good example of our pillar, only build what we need. Breaking up animation into parts through export of Maya layers is a large part of this process. Our pipeline takes advantage of every type of Maya layer structure, even override Maya layers, allowing us the ability to export multiple full body animations from a single file. This allows us freedom, especially in first person, to add multiple animations in a single file independently without layers affecting one another. Here you can see on the slide Bastion's first person SMG reload file. This contains all of his animations for his in-game first person performance. Why do we do this? Well, one reason is that its iteration time is a lot faster. And I'll go through later about how our rig helps support this, but you're able to copy animation layers or animation poses, animation from layer to layer, all without having to go between different files. Having a pipeline that takes advantage of export with all these different layer types really ends up improving iteration speed. So let's talk about how we assemble these assets together with our high visibility performances. Once we've exported our animations, it's time to start assembling the performance itself. Here you can see on the right is Torbjorn's movement performance. So this incorporates the 8 running animations that you see on the left, as well as an aiming suite and a firing animation. So let's talk about how we assemble these assets into the performance on Overwatch. Animators don't necessarily need to work directly with the animation blend trees and state machines 100% of the time. Animators have enough to worry about with the performance itself, let alone dealing with additional complications of server post syncing, animation performance priorities, maintaining performance consistency with the rest of the heroes. We certainly don't need 21 different copies of the same blend tree all doing the same exact thing, and dealing with all the intricacies of scripted animations. Thus, for a majority of our tasks, the animators work in a higher level built on top of the blend trees in what we call the animation blend tree templates. This is a view from our engine TED. TED is the name of our game engine interface. So Torbjorn here, this slide on the picture on the left represents all of Torbjorn's third-person gameplay movement animations. Each box, the purple and blue boxes, are a template, which include animations that make up the performance. You can see I've zoomed in on the right to the third-person 8-way movement template. This is what contains all of the animations and assets from the previous slide that make up the movement performance. A blend tree template is a packaged animation blend tree that exposes specific fields from the blend tree an animator can use to create a specific performance. Templates read scripts, blend multiple state graphs together, play animations, and generally simplify the implementation process so that an animator can focus on the performance. So on the left here, you have a typical blend tree. This is something similar to what you might find in Unreal or Unity or a similar package like that. For those who don't know what a blend tree is, it controls when animations play, how they blend together, which animations override which, and for us, like server-side pose syncing, which animations are playing on the server, and so on. All this information is squished down into what we call blend tree template, which is that little purple box in the middle. Our animation engineer exposes only the values and variables that we need for an animator to focus on the performance. So on the right, you can see the actual UI for that template, where the animations are exposed, how they blend together is exposed, like how fast they play, all the basic properties of performance. So standardized templates are mostly used for common high visibility performances: jump, general movement, crouching, idle, etc. Here you can see a lot of the standardized templates that we have on Overwatch. I want you to look at the top left of the image, though, under the idle section, where there's 2 different templates listed that fulfill the requirements of idle performance: 3P idle and 3P idle simple. So we can swap out standard templates with others that fulfill the same performance requirement, but using fewer, more, or different assets. Reasons for doing this include production cost, required fidelity, and physical attributes on the character. So again, here we have 3P idle and 3P idle simple template. These, again, fulfill the same requirement of idle. The 3P idle template requires a turn left animation and a turn right animation to be authored. The 3P idle simple template, however, only requires a turn left animation to be authored. To get that turn right, the template has built-in functionality to play the turn left animation backwards. So for some heroes this works and some heroes it doesn't. Bastion down there on the right, while he's using his turn left animation, looks pretty good, but when he turns right, you notice he pops up and has a little bit less physicality and weight. So for him, maybe it's not appropriate to use the 3P idle simple template, and we then craft a turn right animation for him and use the 3P idle template. Tracer up there, however, well, her turn left doesn't look half bad when played backwards, so maybe for her, we can just use the 3P idle simple template and use our time to start working on other assets elsewhere. Maybe it's a little excessive to craft that turn right and thus use the 3P idle template. This type of progressive asset creation workflow persists throughout our pipeline and is built into the template system itself. This is the main way we accomplish our only build what we need philosophy. Other generic templates allow stacking of multiple templates together, such as an additive layer template, which allows us to simply add another additive animation on top of existing templates. So it's like Legos, right? we're able to stack templates together and create appealing performances depending on what the ability is or how the character is, their weapons or their physiology. We can add on to existing standardized templates as well as branch between multiple character states, such as when you have more than one weapon or different character stances, etc. So this is Mercy's Graviton Surge Performance template tree. You can see what it looks like down there on the bottom movie clip of what's actually going on with Mercy. You enter a blend tree template set on the right side, so we started the play anim route. Well, let's enter there and move to the next template over called the select by category. This is a template that lets us choose between weapons, so we have the option of branching off for her staff or her gun. So let's go up the ladder again for her staff. We come to an additive layer template. This lets us add on any additive animation to a standardized performance. So in this case, the simple anim template that's being added on is for her floating legs, which you can see there as she's being affected by the graviton surge. And finally, we come to the 3P knockback hover template, which controls her spring aims as she's being pulled into the graviton surge, which I'll talk about a little bit later. So to summarize, to create a new performance, an animator first assembles rough assets in collaboration with the animation engineer in blend tree form. After they're happy with how the character's behaving, the engineer packages the blend tree and exposes the necessary settings and fields that animators can use to bring this performance to other heroes. So we often use templates to separate out parts of the body to play on top of multiple states, like the face. The face template, by default, overrides all other performances and plays facial animations by state. This gives us the freedom from worrying about consistent face poses in each animation file, since the face performance exists at the highest level in the tree, overriding everything else. Generally, we don't even export animation on the facial bones. So on the left, you can see the facial animation template. This includes 3 different sections for animations labeled default, firing, and pain. Sometimes in the blockout stages of characters, we'll just dupe up animations for firing and pain. On the right, you can see the blend tree template set actually expands way left, but you can see that face state machine simple template is plugged into the second highest level of the tree, allowing it to override everything else below it. So for most of our hero production, we control the face animations in one file, rather than in each animation that may need tweaked. So on the left here, you can see Junkrat, who's got his default, which is the default idle pose, which blends into his fire pose as he fires his weapon. This is what we'd typically see at a blockout stage of a character, where you very quickly add in these poses and let it kind of just sit and as we go through our production. When we come to a performance like an emote that needs the face animation worked in at the block-in stages of production, we have controls on each template that allows us to remove the face template override. So this Junkrat emote, animated by Adam York, he's working in at the block-in stages of the character's production. So he has the option of sliding off that facial override template and using the animated faces in his animation file. After the hero has all their suites assembled, we can then spend any remaining time polishing facial animation to all the endgame content and removing the override facial animation as needed. So here on the right, you can see more of a polished default facial animation that's created towards the end of production on a character. So that was our higher visibility performances in the template system. Let's talk about how we use it with our lower visibility performances. As we went through development, we found that there were a bunch of secondary performances that were important for gameplay, but could be considered lower visibility, like charge, stun, knockback, and the other performances that you see here. One of the main benefits of our animation template system is the ease of sharing performances across multiple characters. So again, this is Mercy's combat reactions, not Mercy, this is somebody's combat reaction blend tree set. Includes her gravity bomb, stun, knockback performances, which all use standardized templates, and then the charge and knockdown, which use this inherit template. This inherit template's really neat. What's going on is, it's zoomed in on the right, is that this inherit template reaches into another character's blend tree template set, pulls out that performance, retargets it, and plays those animations on the character, and that's all just built-in functionality to the template. Our animation engineer, Stephen Penson, deserves a lot of props for how easy and invisible the sharing and in-game retargeting process really is. So let's talk a little bit about how some of these combat reactions are actually set up on the asset side. Get hits are created using a single pose for each hit direction, and a spring-based blend to additively blend in hit poses. Through spine rotation and IK manipulation, the hero responds to weapon impacts while keeping their guns pointed in the direction the player is aiming. Layering and offsetting these templates on top of each other allows for procedural motion, which follows the principles of animation. The body leads the motion and the head follows through and overlaps. These 8 poses are driven by our animation spring system rather than solo animations, which are too expensive to author, or physics, which is too expensive on our servers. The gravity bomb and graviton surge and knockbacks also use the spring system, but blends between 5 directional full body poses, plus a shared additive on top for floating feet to simulate a pulling pose. You saw that a little bit earlier. So this video is actually an earlier version of our graviton surge. It's a lot more chaotic than what's in game right now. You can't imagine being sprung across the center like that in game. But you can see how his back or his body is being flipped between different extreme poses as he's flying across the center of that graviton surge. The floating feet's a little more difficult to notice on this performance for him, but it is being applied. After coming out of the knockback or gravity bomb, while the hero is still in the air, the template is set up to blend out to the jump performance. The hero falls and lands as a jump would. So this is built-in performance again to the template. The animator doesn't have to add jump assets to this template in order for the template to know to blend out to the jump performance. While we usually author most shared animations like this floating pose on Tracer, if the shared animation doesn't look great, we can replace them with ones unique to each hero. Again, another example of our only build what we need pillar. So on the right, you can see some of the heroes that we've used, created their own animations with, Diva, Reinhardt, and Soldier 76, but we're still using a shared floating pose for their feet on Tracer. So stuns are a little more difficult, so bear with me to explain, Stuns by default take a shared base upper body stun animation, so a single animation was authored on Tracer, which you can see below, and we've taken the upper body and applied it to the hero. Combine this with the base lower body animation on the hero's default idle pose, so their unique idle pose that the character inherently has during idle. And also adds on the shared additive lower body animation from the shared stun. So we took the upper body, played it full. Now we take the lower body and play it additive. Limb weights control how much influence the additive has on each part of the body. So as you can see here, a shared reaction animation is authored on one hero and one animation is used, and used on other heroes, all while maintaining each hero's unique default idle foot position. So waves take a similar approach by using the current gameplay pose the hero is in, and plays an override animation on the left arm only to fully convey the wave. Again, we make one animation on the character, strip out their left arm, and play it as an override with that 3P left arm override template on the right. An additive animation is layered onto the rest of the body to fully support the waving motion of the arm. So we take the rest of that animation and play it additively. This lets us animate a single wave with the physicality of whatever state the hero is currently in. One animation is created and transformed in export. One additive asset and one full body or base animation asset are created from the same data. The animations are then broken up with bone masks and applied appropriately in the template. So there's some pros and cons to this template system that I wanted to share with you all. To reference some of our values earlier, templates allow for unique character physiology and gameplay while maintaining consistency between standardized performances. It also gives the animator more control over the performance in game. Animators still have the ability to implement custom blend trees if we want, and swap to standardized templates later if another hero needs to use that same performance. When something breaks on a template, like I'm simulating here, I'm disconnecting the anticipation of the jump. You'll notice that issue on all the characters using the template. It's much easier to spot an animation issue across all heroes than in one-off blend trees specific to each hero. So here I'm reconnecting that anticipation. It hot reloads, so it spins, the characters spin around. It's our hot reload animation. And then you'll notice that every character, all these characters using that template are now repaired. So there's some cons to the template system. The templates themselves are currently constructed through code, their interfaces rather, which makes iterating on them a slower process and often forces us to go to our hardworking animation engineer, Steven, for any changes. The workaround is to establish the performance first in blend tree form, which is data-driven and more iterable. And then when we're happy with the performance, migrate the data to the hard-coded template for use with multiple characters. In the future, I hope to construct the interface through data instead of code, allowing more flexibility on how the animators go about prototyping performances and exposing attributes. During peak production, animation needs from design and engineering increased, including help needed with template changes, debugging scripted animations, and new feature setup. However, after having completed a lot of characters at this point, most of the templates are being reused now to use consistent scripts. We are making new templates less frequently, and most changes are tweaks to general templates and exposing variables for the animators to use. After having so many characters done, we're at a point where template adjustments demands on the engineers are becoming less. Issues that arise are generally priority issues, animations interrupting each other when they shouldn't, and adjustments based on any polish changes. Animators are able to support themselves now, having gained more experience with the system. However, we still do deal with bugs like everybody else, and are always looking for ways to improve each performance and how they interact with each other. So we have a few cool tools and features that allow us faster iteration at a higher quality. Investment in Maya and engine tools has allowed us far greater turnaround of artistic feedback to the point where we can often iterate in real time with the feedback provider sitting alongside of us, and we often do. The main tool, of course, we use would be the hero rigs themselves. Maintaining 30 frames per second on rig playback was a fundamental tools goal during early development of our hero rig. It has been key to faster iteration and quick asset prototyping early on. With real-time playback possible in Maya, animators are no longer spending time play blasting from single angles. When we can pull up all 4 viewports in Maya and preview the animation from the front, side, and top angles at once, it really cuts down on the time spent making sure we hit those appealing arcs and adjusting balancing issues. In Maya 2016.5, we maintain 30 to 50 frames per second even in the polish stage when we're adding complex facial animation and other detailed animated controls. But another way we maintain a faster iteration cycle is the ability to trigger the export and reload of animations directly from Maya. So here I'm adding an aim up animation layer to this run performance, or run animation, triggering the export in Maya, and you can see that it almost instantly reloads in game. So here again, I'm disconnecting that aim up layer, hitting the export button in Maya, and a few seconds later, the arms snap down and the animation has been hot reloaded. In the time it takes to play blast an animation, our tool has already exported the curves, built the asset, and hot reloaded an engine. One of the biggest advances on the animation side was how much the team benefited from a switch to code-based rigging. Code-based modular rigging was a collaboration between Dylan Jones, Lan Chang, and the cinematics department's technical art team. In short, Python scripts are executed to create on-demand limb rigs, which attach to skeletal structures that are consistently named across all characters. Only one appendage is actually scripted. If you needed a right arm, the rig builder uses the same code that creates the left. The only difference are the joint angles and a few normalizations of math for the stretching. In reference back to our day one predicament, this approach was a fantastic way to anticipate an unknown universe of heroes, reducing risk and gaining iteration speed and bug reduction. Since scripts broke up the rig creation process, limbs could be added on a per-need basis. It was a process that supported all body types. So here the video starts off with the body torso already made, and Dylan here is unhiding the script that adds the left arm. So here he's reloading the script and rebuilding the rig from scratch. This torso, the limb is not being added onto it. The whole rig is being recreated. So here he's gonna create the right arm. You can notice the code is the same as the left. The only difference is the changing of the names of the joints. He reloaded the script and rebuilt the entire rig again from scratch, now including the right arm. So once a character is constructed, iteration is done only through script. The rig is then rebuilt containing those changes. The tech team doesn't have to doubt or test the rig as much, and animators worry more about the rig hitting the artistic style and less about any technical issues. There's only need to build and script a single limb once for every future hero that needs to use it. This absolutely reduced iteration time and allowed a single rigger to support an entire team of animators for all 21 extremely high fidelity main hero models. So again, if one rigger had to build each arm by scratch, from scratch on Zenyatta here, it would take a significantly longer time than the process we use, which is using the same build script for each of these arms. It was extremely fast. So having a strict structure and consistent naming conventions allowed for complex setups that benefited the art style as well. Non-uniform scale, for example, allowing smear or stretch frames through noodle joints or end of chain joints on the rig was possible because of the network of constraints created through the scripts. Had we been without that network of built-in constraints, we certainly would not have been able to hit a dynamic of an animation style as we wanted with the time that we had. So let's talk a little bit about how some of these built-in features. Parent spaces, for those who don't know, are basically point and or orient constraints built into the rig, switchable through the channel box. They allow the animator to switch the parent of a control to any other control as called out in the build script. This functionality built into the rig is one of the many examples of this being a rig that works for the animator. Our base rig contains a lot of built-in functionality that automates complex setups typically done by animators within their scenes. It eliminates the need for animators to assemble unique complex constraint solutions within their animation files. So on the top left here, you can see that we work the ground plane directly into the hierarchy for the IK feat. This allows us to author uphill or downhill animations if we need to, or versions of performances if we need to. On the top right, you can see we've worked in world orient parent spaces to the arms and the head, allowing them to always point at their target regardless of which direction the spine is rotating. On the bottom left, you can see we're able to separate out the knee from the rig in order to address any knee popping issues or create squash and stretch or smear frames with the leg. And on the bottom right, you can see that we're able to separate out the waist from the spine, allowing more appealing offset in our animation as well as creating funny little dances. To better utilize those parent spaces I just mentioned, the parent space tool allows the animator to quickly and seamlessly alter a control's parent. The parent space tool maintains the position of a control in world space while the animator switches the control's parent. So here you can see that I'm attaching the hand to the hat. Having this constraint solution without parent spaces would mean that an animator has to add this constraint to the file, and now it's hidden somewhere in the hierarchy of the arm. For any other animator that needs to address this file, it makes it much more confusing to find that constraint, and the workflow is just not as clean when it's all consistently implemented into the rig. When used in conjunction with our arm and leg base controls, which are the highest controls on those particular limbs hierarchically, we have the opportunity to create some interesting setups. If you have an arm set to IK and the parent space set to the arm base joint, you can create a sort of IK-FK hybrid mode. You can translate the hand and elbow in IK, but rotate and translate the whole arm through the air using the base joint in FK. Our limb nodes that contain shared channels across all the controls on the limb, for the arms and legs contain a world orient channel. Setting this off allows the arm base to follow the shoulder, its parent. Turning this feature on, however, maintains the world orientation of that arm. This helps immensely for something important like keeping the guns always pointed at your target, independent of what the rest of the body is doing. This setup lets us easily separate out the arms for easier creation of aims. Breaking up rotates onto different joints allows for cleaner aiming, absolutely no gimbal with this process, and eases the process of creating aimed versions of performances. So let's talk a bit about something a little different now, ragdoll and hair. As you've seen in some of the Maya videos and images so far, our character's hair isn't typically animated for gameplay. We take advantage of cloth and ragdoll sim for our hair, in-game cloth and deaths. While we currently use full ragdoll in-game and optionally for one-off sequences, we can animate cloth partially and let real-time sim do the rest, or just fully simulate it. For one-off sequences like our plays of the game, we have the ability to turn off ragdoll simulation if we feel like animating hair and or cloth would give a more appealing performance or the animation is just too quick or complex. Like this play of the game here animated by Michael Biancalana. We had the option of simulating the beard follicles with ragdoll, but in the end decided to hand animate it because one, Torbjorn's moving rather quickly here, and two, we wanted to achieve a much more appealing end time slow frame. With our robust physics system and a bit of tuning, thanks to the work of Aaron Cotto, our physics engineer, and Dylan Jones, our tech artist, rigger, we are thus far able to drive all the deaths off of one animation pose as well. So along with the rig, we have quite a few Maya and TED tools that allow us to implement game assets more artistically, quickly, and generally contribute to a much higher quality of life as an artist. So let's first talk about some of the Maya tools that we use. Our global copy tool can transfer poses and animations across the same or separate Maya sessions through XML, writes the poses to XML. As you can see demonstrated here, it can copy and paste poses or animations in world or local space, by selection order, or by name to multiple characters. We have a very customizable picker system that works in conjunction with the consistent naming conventions of our rig. After using the GUI to create different shaped, colored, and sized buttons, one click assigns a namespace, and you have access to a fully customizable and shareable layout of controls. Controls can even be set up to be stepped through for quick access, and animators have the option of adding multiple objects to one button, or even adding Mel or Python commands to make custom tool panels. So here you can see I'm moving different buttons around the UI and selecting multiple objects to add to a new button to create a very fast quick select set. Another quality of life tool is the finger pose tool. The finger tool quickly adds and subtracts specific rotations to finger joints using quick keys that are set up to mimic the rotations fingers go through to form standard hand shapes. After assigning the namespace, an animator can quickly form hand poses from the bind pose, using conjunction with a pose library to quickly offset mirrored hands, and perform minor incremental adjustments to one, some, or all fingers on one or both hands at the same time. The mirror animation tool takes mirroring poses to the next level, allowing for quick iteration on animations like cycles. Here I'm demonstrating the creation of a cycle. Our typical workflow for a run cycle is to quickly block out the main poses by taking advantage of our mirror tool. Block out the poses for the first step, copy and mirror for the second step. When polishing, we can simply work on a single side of the animation, and the mirror animation tool can quickly offset that animation to the other side of the character with a press of the button. Copy the first frame to the last, and we've got a run cycle with perfectly mirrored limbs. Lastly, the movement generator tool brings game data like jump impulses directly into Maya. We can animate to those game-driven translations and exclude the motion and export. On the left, you can see the Maya animation layer called jump height, which contains the impulse data pulled from the game. The left Widowmaker is how an animation looks when animated in Maya. The top right layer panel shows the jump height layer turned off. The Widowmaker on the right is what's actually being exported. You can see that her feet go through the ground as she's being counter-animated to create the anticipation. In-game, the jump height is reapplied through the impulse we pulled out initially. This allows us to produce content in a non-destructive workflow that looks correct both in Maya and in-game, while allowing designers and engineers full control over the character gameplay movement still. The tools team has been amazing at providing engine tools, allowing us to not only assist in the ease of implementation and hero setup, but to quickly iterate and break down performances into individual animations in a way that echoes animating in engine. One such tool is the animation debugger, based off an idea from Autodesk's Skyline project. It allows the recording and breakdown of a set of performances from an active play session. As you can see here, I'm recording a performance of 76, running around our test level, firing, reloading, and jumping. When I'm done recording, I simply hit stop recording. You are then presented with a timeline view of all the animations that played, how they are stacking when they play, and blend times, which are shown ramping up and down in blue. Selecting clips in the timeline gives options to take you to the associated blend tree for easier debugging, or for finding the animation in the asset browser. Combine this with the quick export time of our Maya export tool, and it's fairly close to animating in-game, but still using the Maya user interface. And as a side note not shown in this video, this debugger allows hot reloading, so an animator can make tweaks in their animation, hot reload, and see the results in the recording without having to manually recreate the performance. So let's talk about the future. Well, there's room left for improvement, of course. There's still plenty left to do. In the future, and as mentioned earlier, I'd love to get our templates data-driven and potentially give animators the ability to prototype performances and expose some settings themselves. I mentioned a few times about how we used springs to blend between additive poses for get hits, gravity bomb, the graviton surge, and knockback animations. There was a talk at GDC 3 years ago from David Rosen at Wolfire Games about his spring transitions and overgrowth. This gave me a lot of ideas for getting a lot more fidelity in our transitions between states. Even expanding upon this idea, we could break up the transitions based on limbs and achieve a lot more overlapping action through each state change. We unfortunately have to deal a lot with server-side pose matching, which limits a lot of the things we can do with additive and procedural animations, and ragdoll. But I'm constantly looking for new opportunities to try it out, especially in first person where the animation is on the client only. Very early on, we had a prototype for non-camera space motion blur to give a real visceral feel to the movement and gameplay. The idea for this consisted of two parts. In the top right images, the physical geometry of the mesh is stretched along the vector of movement, essentially to automate smear frames based on the speed the vertices were moving on screen. The bottom images added onto the tech from the top to blur parts of the character model based on those vectors. The top left animation is a prototype I did with a custom tracer rig. Instead of one noodle joint we currently have running through each section of the limb, we had 4 joints running through each section. This allowed me to translate the sides of the mesh instead of scale, which allowed me to get more precise and appealing smear shapes. It's something we'd like to expand on more eventually. So in a quick summary, we went through, that's my talk, sorry. We went through how some of the animation team pillars and Blizzard cultural values influence the direction of the animation pipeline, such as only build what we need, keeping the team smaller, a handcrafted art style, an animator being responsible for the in-game performance. We talked about how we use layers and break up our animations to reduce overall asset count, how templates helped animators reduce the complexity of implementing the hero performances, how iteration time is significantly reduced with a rig that works for the animator, tools that improve quality of life, letting animators better focus on the performance, and lastly, some thoughts for the future. I wanted to give a special thank you to everybody on Team 4 who helped me practice my talk, and again to Team 4 for creating this game. Lastly, I speak for the entire animation team when I say how thankful we are to work with such a talented and genuine tech art team, our diligent and patient animation engineers, our world-class design and engineering team, and the rest of the talented artists and engineers at the studio of whom we draw reference from daily. If you had any questions about this presentation or feedback, feel free to email me at jesse.davis@blizzard.com. You can follow me on Twitter at jdavisanimation. And I believe we have 10 minutes left for questions, if anybody has any questions. Thank you. We'll see. Going once? Oh, yeah, there we go. Hey.
When you're bringing a new animator onto the team, could you describe the way that you train them up on this new system? Because it seems like it would be quite a change for a lot of people to get into it.
Slowly but surely. We're not, like I mentioned, it's quite a process to bring somebody new on, which is just part of the trade-off that we made.
Okay.
It's just to gain experience. We start them off slow, of course, like any animator would be started off slow. Let them train up with more basic implementation stuff, and as they grow on our team, they're exposed to more of the particulars of our animation system. So.
Okay, thanks.
Yeah. Hey.
Hi, I had a quick question about if you noticed any issues with animation compression, since this is an online game, any sort of artifacting, and who in the pipeline that falls to, your animation engineers or the animators, because they have an expanded role?
Sorry, I'm supposed to repeat the question too. He has a question about animation compression, who that falls onto, and that's it, right?
Yeah, or if you just have like tools that you guys use to kind of simulate various network speeds and things like that, so you can see whether your animations are failing or not in Engine.
Well, we are fortunate enough to not have to deal with any of that.
Awesome.
We have it's built into our template system. That's again another built-in functionality to that. We have a whole team, a live ops team. Well, that's live ops. We have a whole perf team dedicated to going through the entire game, not just animation, and checking the performance of level assets, animation and stuff. Our technical director now, who was originally the lead software engineer when he worked on this, or our lead graphics engineer, was the one that implemented the compression. And it's been something we've used for quite a while. As it's no secret that this project evolved from Titan, and it's something that we started on there and have evolved as we've gone through.
Okay, thank you.
So it's not super specific. I'm not the most technical in animation compression, but hopefully
That's fine, thank you.
Yeah.
Hey, first off, thanks for the talk. It's fantastic.
Thank you.
I'm interested the amount of use of the layers in Maya, and obviously being anim to anim per character. How does your constraint systems work from layer to layer, being that they look quite detailed, weapon types and things like that?
So how does our animation constraint system work with layers in Maya?
Yeah.
So as long as you add the constraint to a Maya layer is just a way of like breaking up translations and booleans and string-based channels and enums and so on. So it's not anything that, it's either a 0 or 1, right? Like it can either be a 0 or 1, or if it's any other number, it's usually 1, or it defaults to 1. So when you add or subtract that to that number, you're in Maya layers, it's just adding and subtracting to a 0 or 1. So there's not really any sort of breakdown of the constraints when we're using layers.
Okay, but is the information for the constraint added to the base layer and then it's then edited per layer, or?
Yes.
Yeah, okay.
Yeah, so we, in our default pose for the file, in our base animation layer, we'll have the set values for the parent space or the constraint, and then if we need to, we can change them in the Maya layer if we're doing something different. We do that a lot, actually, especially in our first-person stuff.
Thank you very much.
Yeah, no problem. Thank you. Hi.
Hey, thanks for the talk. It was a great
Thank
talk. Ever since seeing the How Our Hero is made, I definitely wanted to see the rigs. So thank you for showing those off in great detail. I wanted to go ahead and ask, you guys have a lot of like repurposing for, pay for what you need sort of thing, and build what you need. So you reuse a lot of animations between characters, or your tools that you're able to easily select different joints on a character. How does that work for unique bones on different rigs?
So our rig is consistent through all of our characters. So we can, and we often, if we need to reuse an animation, we simply replace the reference with the new character. And then all the translations are local to, with most games, are local to a main joint. So everything kind of, most of the time, unless it's IK, obviously, with like with a world parent space where the translations are relative to the world, then it'll port off of the local translations of the pose.
So special limbs such as like Zenyatta's extra arms and stuff like that, that's only for special animations and wouldn't be used for anything like that?
Zenyatta's arms is like a prop that we attach onto Zenyatta's back.
I see.
And that's animated just for that one sequence.
I see. So all of your characters are restricted to working with the same rig set?
Yep.
Okay.
Well, that's generally 80% of the rig, and then of course each character has their own detailed joints and little appendages and stuff unique to their character, and weapons are of course all different. So
Great.
But we have the ability to add in our build scripts the option of adding on multiple limbs,
I see.
like tails or something like that.
Thanks.
Thank you. Hi.
Hey, how's it going? My question is about the smear frames. It seems like the animation style in Overwatch is heavily reliant on the smear frames to create character. Do you have any sort of problems with bone scaling? I thought I saw a slide that said that only non-uniform scaling was allowed on leaf joints.
Yes.
And then the rest was what using the constrained space switching, or what kind of considerations went into like doing smear frames in Overwatch?
So what kind of, sorry, can you repeat that last part? Which?
I guess my question is mainly about joint scaling in game.
Yeah.
Is it correct that you guys only have non-uniform scaling on leaf joints, and then the rest is more just translation based
Okay.
for smearing?
Sorry, so do we only have scaling on leaf joints? We do because inherently in game, in FK, joints don't have any kind of idea of what's happening to the joint above it. It's always inheriting these transforms. So when you scale a joint, it'll translate in game that joint away from it, but the joint size won't change because it's not being scaled itself. In Maya, actually, the joints are a little smarter than in Engine. They know to scale along with its parent. So that's why when you scale a skinned rig's joint, the child joints scale as well. So that's why we can only use leaf joints to, and for those who don't know what a leaf joint is, it's the joint at the very end of a chain. We've constructed our rig as such that as you go through an arm, for example, there's a bunch of leaf joints that the mesh is actually skinned to. It's not skinned to the elbow joint that rotates like this. It's skinned to joints that are children of that elbow joint. So we can scale those leaf joints to create the smear frames.
Oh, okay. Thanks.
Yeah, no problem. Thank you for your question. Cool. All right. Got a little early. Thank you guys for coming.